Good morning and welcome back to Dr. Logic Awkwardly Does Correspondence Proofs in Modal Logic. This is the third one that we're going to do, but at the very end, I'm going to give you an example that you can work through on your own. It's going to be very similar to the one I'll talk about in this video, but it's also available in my textbook if you want to work through the details, check your own work, see if you've got a good understanding of what's going on. So this time, the frame condition that we are going to look at is slightly more complicated than ones we've seen before. This is going to be the condition that is called being Euclidean. And the way that you can kind of remember that this is the Euclidean condition is that it describes triangle forming. So the condition is for every x, every y, and every z, if x sees y and x sees z, so you've got a branch, then it follows that y sees z. So schematically, you've got something that looks like anytime that you've got a branching path that goes up from x, you can close it off and make a triangle. Now, because this is universally quantified, the fact that I picked this to be the world that stands in for the variable y and this to be the world that stands in for variable z means that I got the arrow from y to z. But because this holds for any set of arrows, if x sees this world, if x sees this world, then this world will also see this one. So in the end, you get, every time you have a branch, you've got arrows between the kind of ends of the branch to pull it back to a triangle. This frame condition is going to correspond to a formula that we will call E, because it's for the Euclidean property, and that is possibly P implies necessarily possibly P. So our lemma is some frame F is Euclidean. That means that it satisfies that frame property if and only if the formula possibly P implies necessarily possibly P is valid on the frame. So we have to go both directions, as always, going from the frame condition to the validity of the formula is the easiest one. So we will start with that. In this case, it is the left to right version. So we start off by assuming that we have a frame F that is in fact Euclidean. And then assume that it's not valid on this frame. So the negation of the consequent, but that on this frame, necessarily, possibly P implies necessarily possibly P is not valid. i.e., there is a model M on F and world W in M such that at that, I'll write it over here. At that world, we can falsify possibly P implies necessarily possibly P. i.e., let's just go over here and start building our model. Here's W. This means that possibly P is true, but necessarily possibly P is false. In order for the possibility claim to be true, W has to be able to see a world, let's call it W prime, where P is true. So that takes care of that one. Now, for necessarily possibly P to be false, this means that possibly necessarily not, possibly necessarily not P is going to be true. So all I've done is I've just done a little bit of modal interchange on this formula to get something that is phrased as a true formula. This is also a possibility claim. So we need to make another world, let's call this one W prime, where necessarily not P is true. And now you can see that what we have here is something that is the kind of starting point of the Euclidean relation. W is our X, W prime is going to be our Z, and W2 prime is going to be our Y. Because as you can see, what we want is we want to be able to get an arrow from this world to this world, because there comes our contradiction. If necessarily not P is true at W prime, that means not P has to be true at W2 prime. Then it has to be true at W prime as well. But you can't have both a formula and its negation true at a world at the same time. Now, we also have the arrow going the other direction, but that isn't necessary for these purposes. So this shows that if you have a Euclidean frame, the assumption that there is some world that falsifies the axiom leads to a contradiction. Let's consider the other direction. And again, we always do the contrapositive. So what we will do is assume that F is not Euclidean, and then we will show how to construct a model that makes the axiom false on the frame. So if we've got this frame that is not Euclidean, then what we know is that there is some W prime, W2 prime, such that WC is the first one, WC is the second one, and in order to block the Euclideanness, we know that neither W1 sees W2, nor W2 sees W1. So what we get is we have something that looks like this, where, and what I'm going to do is I'm just going to kind of do this, but then cross it out. It's hard to indicate kind of lack of a relation, but hopefully you can see that what I'm saying is here are these worlds and they definitely don't see each other. So let us define our model this way. So we need to have a model M on F as follows. We will say that at this world W prime, the value of P is true, because then it follows that at W, P is possible. So that gets us the antecedent of our conditional. Also, we want it to be the case that, so where X doesn't equal W prime, so all of the other worlds in the model, the value of P at that world will be false. Now, the first thing to note is that this is a consistent valuation because we say at W prime, P is true. Everywhere else, it is false. So this is a consistent and classical valuation, doesn't provide us with any difficulties. However, consider W2. If it sees nothing, then at that world, necessary not P is true. If it sees at least one world, so if it's not a dead end, then every world it sees makes P false. And this is because the only world where P is true is W prime, and it can't see it. So in that case, it is still the case that necessarily not P is going to be true at W prime. But then it follows that we have possibly necessary not P at W, which falsifies the axiom. QED. So again, if the frame is not Euclidean, then you can define a model that makes the axiom false. So there is your third correspondence proof. And I told you that I would give you another one that you can practice on your own. So I will clear everything here. Consider this frame property, convergence, which says for every X, for every Y, and for every Z, if X sees Y and X sees Z, then there is some world W such that Y sees W and Z sees W. So what we have here is any time that you branch going forward from a world, you will always eventually come back and converge. So this is also often called the diamond property, because look at the pretty diamond you made. This is going to correspond to an axiom that is named for Geach, because he was the first one who kind of systematically investigated it. And that is that possibly necessarily P implies necessarily possibly P. So you can see that convergence is very similar to the Euclidean property, and the Geach axiom is very similar to the E axiom. Hopefully that, along with the proof that I've just given you, will be enough for you to kind of figure out how to prove the correspondence of the convergence property and the Geach axiom. And that is your homework assignment. Next time, we will talk a little bit more about, I don't actually know what we'll talk about next time. Probably not more correspondence proofs. So join me next time for a modal logic surprise, because I haven't decided what I'm going to say next. Until then, take care. See you later.